for the second day. So we will have some visuals of rocks, sandstone, and also carbonates. And then we will review the well hydraulic system, Dorsey equation, and skin factor also will be detailed out. We will review some three diagnostic tools, DST, induction logs, and also well test. And also we will go through the challenges in carbonate acidizing. Moreover, we will review the limitation of using HCl and also the placement via cold tubing. There are two things that you will be interested. I think the stimulation in horizontal wells and what are the differences between these two. When we do stimulation for horizontal wells and vertical wells, what will be the actually basis and the candidate for these two situations. And then what are the differences also between acidizing in oil wells and also for the gas wells. So that's why the main difference, which is diversion, will be discussed in details. We will go through the damages that can created from stimulations, and we will review the additives, acids, and also the compatibility with water. Also, we have a fine migration case study and a technology that I'm going to show it to you, and how this technology can be used with matrix acidizing. Also, the mineralogy of the field will be shown in a slide, and how this fine actually migration and fine stabilizer is working will be also shown. There will be a field example, and then finally I'm going to wrap up the presentation. Okay, so this shows you a sandstone samples with specific gravity of 2.48, and normally the porosity of sandstone is about 10%. So as all of you know, sandstone is a clastic sedimentary rock composed mainly of sand grains with the sizes of 0.0625 to 2 millimeters silicate grains. So the next slide is showing to you an unconsolidated sandstone. So as it implies from its name, it has poor cementation, high porosity, and low strength. So sand production is more likely to occur during exploitation. So that's why here you need to make sure when you do stimulation and have sample from this unconsolidated sandstone, and you actually identify the type of cements inside this sand to prohibit further sand production from your reservoir. So regarding the carbonates, carbonate rocks are a class of sedimentary rocks composed primarily of carbonate mineral. There are two major types. They are limestone and dolomite. Limestone is composed of calcite or aragonite, okay, and dolomite rock, which is composed of dolomite mineral. Okay, so this is visuals of typical carbonate rocks. Okay, well hydraulic system. This is very, very important for you to master. Actually, it's not only for you to go through the stimulation process, but this is all for all of us as petroleum engineers. So well hydraulics help us to understand the process of flow to the well from the reservoir. Okay, so it is important here to distinguish between well inflow productivity and also well production. This is because an improvement in the well inflow performance, okay, which is from the reservoir to the well, can have only a limited effect on the daily well production in the well outflow. Is limited by tubing, as you can see here, we have the well outflow. Let me show this by a laser. So we have a well outflow here, and I don't know why it's lagging, but seems that okay. So we have the outflow and we have the inflow. As you can see, we have the pressure, reservoir pressure, and we have actually the flowing reservoir pressure, and the difference between these two will give us the drawdown. We have several completion generally in our well that we need to account for the pressure drop. Okay, inside the well, we have the surface facility, surface choke, and the pressure drop. So all this calculation needs to be done in order to come up with the pressure drop inside our system, and finally to conduct the nodal analysis and the sensitivity that is needed actually for our case. So they need to consider the flow path from the reservoir boundary to the production storage facilities as a complete production system, which is shown in this figure. Okay, so Darcy law describes well production or injection in a steady state flow. So rearranging the equation, this equation, as you can see, will show very clearly the rule of the scheme factor, okay, as an additional pressure drop in the near wellbore region. So as you can see, we have two terms here. We have the second term, which is the skin here, whereas the first term refers to the expected pressure drop according to the Darcy law without any damage, and the second expression in equation number 2 show the additional pressure drop due to the skin effect. So taking a look at equation 1, we can integrate the skin factor into a logarithmic, okay, into a logarithmic expression in order to consider the scheme factor when looking at the relationship of the radii. What we get is so-called apparent well radius, whereas RE is the outer boundary radius, RW the well radius, and RWA is the apparent wellbore radius in meter. Okay, so in equation 3. So when we solve equation 3 by applying the power of E leads to equation number 4. Okay, taking a look now at equation 4, we can easily see that a low or even negative scheme factor on one hand reduces the pressure drawdown in the near wellbore region. On the other hand, simultaneously results in a large apparent wellbore radius, which naturally increases the productivity index. In other words, the damage is being removed or overcome, and this is generally achieved by stimulation. Okay. So this is this slide shows you the skin. The skin is defined as the additional pressure drop in the near wellbore region. The total skin factor consists of several components. So all the components here are shown and included. We have total skin, we have damage due to the invasion by drilling mud, we have skin due to the perforation, skin due to the gravel pack, skin due to partial penetration, skin due to the turbulence or non-Darcy effect, and skin which is rate and time dependent due to the changing gas saturation, and skin effect due to the slanted wellbore. Okay, so this is show you the total skin factor that we need to consider when we going for a stimulation. Of course, doing a stimulation is only can remove the SD, which is the damage. So this is shows you a DSD. Okay, so as I told you before yesterday, we have several diagnostic tools, and DSD is one of the actually diagnostic tools that we can use when we're drilling a well. So the characteristics that identify the damage in this curve are a short radius curve in the CDE situation. So as you can see here in the CDE, we have a short radius, okay, in the curve, and almost a flat along DE. So this is a flat showing that actually there will be this is an inflow. Actually, there will be a limited actually rate from our reservoir to the wellbore. So after that, we can have an increase immediately after a closing period as an EF. So as you can see, there will be an increase of pressure after closing until the F, and a large differences between the closing pressure, and you can see there will be a large differences between F and G. So a flat region in DE, increase in pressure in EF, and the differences in pressure in F and G are some indication that we have damage in our well. Okay, and this is conducted via drill stem test. Okay, so this is showing you an example of DLL, a log, induction log. This shows a good separation of the LLS and LLD from each other. So as you can see, we have three charts here: LLD, LLS, and MSFL. So differences between these can, semi-quantitatively give us the actually the region of the permeable formation. Okay, so the penetration of the filtering mud drilling can be also calculated through the responses of these resistive or conductive logs of shallow, medium, and deep devices. So these answers will give semi-quantitative indicators of the possible impact of the damage on well production. So the invasion radius could be determined if one of the curves has a different value when compare the other two. So how a well test? Because I'm going to show you actually well test that can contribute to a diagnosis of the skin. So here in this slide, I'm going to show you how a well test will be conducted. So as you can see, we are lowering a sensor into the well, and then we need to measure the Q and also the pressure. So here in this case, we are shut in the well. So as you can see here, the pressure is going to be stabilized, and the Q is 0. And after that, you can see the response. The responses will be recorded via the sensor, and as you can see, the pressure is increased. And this is somehow typical build-up test. Okay. So in the next slide, I'm going to just show you how pressure transient analysis or testing can be used for coming up with the damage. So this is a powerful tool for reservoir characterization. And the following information, as you can see here, can be extracted from well test: permeability, skin, average reservoir pressure, deliverability, potential, reservoir description. For example, if we have a fault, what is the distance between our well and the fault, and also do sampling. Regarding the skin, we can see whether the well is damaged or stimulated. So most wells are either damaged or stimulated, and this has a direct effect on deliverability of the well. So the skin is a measure of the completion effectiveness of a well. A positive skin represents damage, while a negative skin represents improvement. So how we can actually come up with the diagnostics? As you can see here, we have different regions. We have early time region, we have middle time region, and we have late time region. So what we can do here is we can have actually we can come up with the skin by doing analysis on the middle time region. Okay, so the middle time represents radial flow, and it is not until middle time is reached that permeability can be determined. So after that, we have equations, and from these equations we can come up with the scheme here. From the vertical location of the flat, so here, as you can see, from the vertical, we have the derivative and the pressure. And from the vertical location of the flat of the derivative, these two answers should be the same. So the larger the separation between these two, the pressure and derivative curve in the middle time region, the most positive is the scheme. So there are, very interesting actually diagnostics that you can perform in this actually in this area, and I hope that we will have time to go through this diagnostics, which is specifically meant for weather stimulation. So carbonate acidizing challenge. So this is the challenges of acidizing carbonates. So the first thing that we need to know is that acidizing in carbonates, require periodic treatment to maintain economic production. Some of the production facilities create, additional challenges for successful acidizing treatment, including significant reservoir pressure depletion, high water cut, formation heterogeneity with high or low permeability strikes, low reservoir temperature, crude with tendency for emulsion and sludge creation, and enormous thief zones created by previous acidizing treatment. In many cases, uncertainty in the formation properties make the stimulation more complex. So what are the solution? There are several solutions, and we can have for this, for example, the first of all, we can have a good diversion. We can have actually the placement, doing the placement via coiled tubing rather than doing it by ball head, and also having nitrogen or CO2 for the flow back. So here, QA/QC is very, very important in order to make sure that the acidizing treatment is going to be conducted safely and effectively. Moreover, laboratory work such as core flow testing and other tests. Other tests will be very important to clarify the post-treatment aspects. Okay, so this shows you the the challenges in HCl or let's say HCl limitation. So when we use HCl, there is an aggressive corrosion at high temperature. So the spending is rapid in carbonate stimulation. So there will be a tendency to have a sludge. Of course, when we have the when we do SARA test and we know that the asphalting is high, there is a tendency to create some to have some sludge created there. And also we have HCl sensitive minerals. So there are some cements that holding back all the rock structure. So if we don't know about those cements, and if those cements are sensitive to HCl, there is a risk to cause some sand production and fine migration in our reservoir. So placement with coiled tubing. So placement of so the challenge, of course, in performing acid job is ensuring that the acid goes where it can do the most good. So to facilitate placement of the acid across the entire target interval in the well, operators often use coiled tubing units. So a coiled tubing unit is a specialized piece of equipment that utilizes a real mounted tubing string that can be run concentratedly inside the well production tubing to the point directly across the interval that is targeted for the treatment. So the acid is pumped through the coiled tubing and into the productive formation. So this equipment allows precious placement and pumping of the acid. It also provides the added benefit of not exposing production tubing to the acid. Okay, so for your information, if you use ball heading, that means that we pump the acid straight from the wellhead inside the perforation and also inside the reservoir. The risk of actually entering the iron inside and other rust and precipitates inside the formation is high. So that's why coiled tubing is the main or let's say the safest way to for placement of the acid inside our reservoir. Okay, so here there is actually a question that what are the differences between doing stimulation in vertical and in horizontal wells. So this figure clearly actually shows you. So as you can see in the vertical, we have the production, and this figure is similar. We have the skin in our horizontal axis, and you can see the skin is from 5 to 20, and we have also the production. Each line here is showing you the horizontal permeability and also the type of the well. For example, starting from below, we have vertical well, and the horizontal permeability is 0.1 millidarcy. Going up, it's actually same vertical well, and we have a horizontal well with the third one. We have a horizontal well with a length of 500 feet and horizontal permeability of 0.1. So we've done actually a sensitivity analysis by using zero steady state equations, and from that we come up with this, that in general, actually horizontal wells that are not hydraulically fractured are relatively more attractive than vertical well if the vertical permeability is larger or if the reservoir thickness is small. The requirement of good vertical permeability is relaxed in a thinner formations. That's why I'm saying we need a thinner formation in horizontal one. For the matrix stimulation of horizontal wells, the selection of candidates follow the same criteria as for vertical wells. And also we are expecting the post-treatment performance, same. While wells that are candidates for hydraulic fracturing must be cemented and cased for the appropriate zonal isolation, which is very important. And the spacing, of course, of the induced fractures, those that are to be matrix acidized can be open hole, slotted liner, or pre-perforated liners. Of course, they can also be cemented, cased, and perforated if completion consideration are indicated. As I told you before, the use of coiled tubing is recommended for matrix stimulation in horizontal wells. This technique can provide the necessary mechanical isolation and diversion for uniform coverage along the horizontal well. For carbonate reservoirs, injection of acid without coiled tubing can result in adequate coverage and an unsuccessful stimulation. For a vertical well, in this reservoir, as shown by this actually right figure, and for permeability as high as 1 millidarcy, the maximum production rate is about 46 stank tank barrel per day, as shown here. This is the maximum production rate, as it's shown here. As a result, vertical wells with permeability less than 1 millidarcies are candidates for hydraulic fracturing only. For a 500 feet horizontal well and horizontal permeability of 0.5 millidarcy, the maximum production rate is shown to be about 180 barrels, which may still be unattractive. Okay. However, for a 1,000 feet horizontal well with the same horizontal permeability, the maximum production rate could be as high as 360 standard barrel per day, which could be attractive for a stimulation. So for all calculations shown in this figure, this common anisotropy leads to so this is all the equation taken from Joshi and Economides' book. So the result will be more advantageous, of course, for horizontal well. This conclusion is that long horizontal wells may be candidates for matrix acidizing rather than hydraulic fracturing. In reservoirs of reasonably low permeability and permeability, isotopies, and reasonably small reservoir thickness. Okay, so this shows you how we can come up with a sensitivity analysis and candidate selection for horizontal and vertical well. Of course, in a detailed workshop, we are going to do this in Excel file and do some exercises for different wells with different properties and KH versus KV. Okay, matrix acidizing. Okay, so what are the differences between matrix acidizing in gas wells and oil wells? Okay, so the acidizing process differs in gas wells compared with oil wells or water injection wells because of the two-phase gas liquid flow during acid injection and also because of the relatively low viscosity of the gas. So here we are demonstrating the differences, that affect the penetration of acid into the formation and the distribution of acid along the wellbore. So when we use acid, acid will displace gas in the formation around the wellbore. The favorable mobility ratio between the acid and the gas will lead to a piston-like displacement of the gas by the acid. However, behind the acid front, a residual gas saturation will remain. A study shows that the impact of residual gas saturation increases acid penetration into the reservoir when compared with a single phase displacement process. On the other hand, the large contrast between the viscosity of the acid and the gas in the reservoir may be beneficial to better distribution of acid along the wellbore. Because the acid is much more viscous than the gas, there will be an increased pressure drop wherever acid is placed in the formation. So this can, function as a natural viscous diversion. As acid enters the higher permeability zone, the increased pressure gradient can divert relatively more acid to lower permeability zones. Okay, so here, we showed that doing acidizing in gas wells will be, showing better results in oil well. That's what, due to the differences in viscosity between the acid and the gas. Okay, so what will be the damages from stimulation materials? Stimulation works also can create more problem than the disease also, particularly in the relation to the material use. So we use acid, additives, and incompatible water. These are the main, the main component that can create damage. What are the damages from the acid? So normally, why we use acids? In order to increase the production. So using mud acid in the acidizing process cause precipitation of different materials such as organic deposits and inorganic precipitation. So HF, which is the mud acid, can dissolve the cementing material. So when this happens, there will be a decreasing in the strength of the rock, and there will be migration of the sand. Then we will have positive skin and total collapse of the formation. There are cases where the formation is collapsed behind the cement. So that's all because of the removal of the of the cements, natural cements, and decreasing the strength of the rock. So formation of a stable emulsion, which cause low pH, and low pH will create some rigid films, and this will cause also increase of the skin in our well. So how about the additives? So normally we add this kind of additives to perform specific functions during acidizing treatment. So what are the functions? As listed here, we can, have a fluid loss additives, friction reducers, corrosion inhibitors, demulsifiers, and gelling agents and sequestering agents. Okay, so the problem that created by additives on the first one is demulsifier formation, which is formation of stable emulsions. Chemical reaction, when we have additive contacted with, have contact with the hydrocarbon, there will be precipitates, and these precipitates will clog the pores, and also this can create positive skins. So finally, we have, we need to know that additives themselves also can cause clogging, and this will increase the skin accordingly. So when we use incompatible water as a spacer or post-flush or other kind of as a base fluid in our acidizing, because of formation water contains some dissolved salt, there will be some actually reaction that can happen between these two. So water sources introduced to the formation are the injected water, workover fluids, and water flooding that we use in OR and other actually works. So there will be, of course, precipitates, and this can cause buildup of the scale in the wellbore and also in the perforation. So these kind of scale are easy to treat than formation damage. Okay, so here I'm going to just show you some info about fine migration and how this fine migration can contribute to actually reduction of our production. So normally the thing that we need to know that when we the subterranean formation or subsurface formation, sometimes they actually specifically in sandstone reservoirs, there are some uncemented fine particles, and these uncemented fine particles include kaolinite, illite, feldspar, and other type of carbonates. Okay, so when we produce from our reservoir, we will induce some drag forces, and these drag forces will be created by our drawdown. So here, this kind of these materials or uncemented fine particles will be more actually transported. So lifting, migrating, and plugging of the formation. This will be the outcome of these fine particles. Also, they can plug the gravel pack. Okay, so fine migration is the well-known problem in sandstone formation. So reduction in permeability, even we have 10% productivity can cause a lot of capital for our actually well. Fine migration problem may be treated by reducing the production rate, okay, increasing flow area by high density perforating, open hole completion by having horizontal wells, fracturing to reduce the interstitial velocity, and also using chemicals, fine stabilizer to adhere the mobile fine to the pore surfaces to reduce the propensity for the mobilization. So that's why here the later method is a well-known and depends on well-damaged characteristics. So it can be utilized as a standalone treatment or in conjunction with stimulation treatment. Okay, so here I'm showing you actually a mineralogy of a sandstone reservoir. This is a case study. As shown here, we have several zones. Okay, we have E11, E12, E12B, and other. And for each zones, the total clay, quartz, feldspar, and other type of minerals are indicated. So this is a quite actually a very important actually materials in order to come up with the right volume of acid, the right concentration of the acid, and actually the design that can be done here. The majority of the design that will be conducted by softwares is based on the mineralogy and identification, the type of the damage that is there in our reservoir. That's why it's very important to know the, for example, to know the swelling clay such as elite and kaolinite, and also to know the clay that have iron such as chloride, and key in these data to the software. Okay, so this will give us a very good, so because if you don't have such information as a mineralogy, using software will be garbage in and garbage out. So there will be no actually good results, and the stage that can be created also by the software are not accurate. Okay. So this is showing you actually stability. If we have clay, for example, so what will be the stability of certain clays with the temperature? That's why this is very important for you to, first of all, the mineralogy, and second, you need to know that actually studies that shows that clay become unstable in HCl at different temperature. So stability of such clay, such as for example, smectite and mixed layers will be unstable at 150 degrees Fahrenheit. So that's why if you have chloride, then you need to know that the temperature that you can, the chloride will be unstable is 125. So this is a very good information that can be used in conjunction with the mineralogy to design your stimulation treatment. Okay, so this is a technology that I'm going to show you how the fine stabilizer is going to work. There are two mechanisms that needs to be understood by you. Is that the mechanism of coagulant and the mechanism of the flocculant. So in the coagulant, there will be, because this chemical has a positive charges, so this will be actually, and then we have clay and fine, they have negative charges, so there will be an attraction that can happen between these two, and there will be actually this can cause this fine clay to adhere to the pore spaces. And we have flocculant, so there will be long chain flocculant compound that will be agglomerate, the microflux. In the right, you can see the result that is conducted in a laboratory and showing you the zero potential and the turbidity of the product. So as you can see, the KPI for zeta potential is to have the negative to positive charges between 0 to 5 millivolt, and for the turbidity, which is the measuring the clarity of the fluid, it should be less than 5 NTU. So what are the outcome of this fine stabilizer? which is a chemical, is to reduce the fine bridging in the formation pore throats to improve the critical drawdown. So what is the critical drawdown? Is the drawdown that beyond that number there will be drag forces, and there will be sand production. That's why normally we need to respect this critical drawdown. And so another advantage is that we can reduce the formation damage, since we are coupling this coagulant and flocculant properties. There will be there will be no lifting migrating of the fines. That's why we can have this, and then we can prolong the structural integrity of the formation by keeping the fine at the formation well. So here you can see that in the normal production, we are producing the fine. Fine will be produced. So here is our in the right side is the well, and the left side is the reservoir. So normally we are producing the fine when we don't have any fine stabilizer, or when we normally have a formation that have clay and fine inside it. So the blue circles are the fines that normally will be produced to the surface. So what we do normally is to inject fine stabilizer in the second stage. We are going to inject, okay? And then we will squeeze this, and for some time, normally 12 to 24 hours, based on the characteristics of the fluid and also the formation. And after that, as you can see, we will backflow, and there will be attraction between particles, and all the fines, not all, but the majority of them will be adhered to the surface of the pores, and the fine migration will be reduced, to the surface. So this shows you a simple, description, visuals of how this fine stabilizer is working. So this is the operational process scheme. As you can see, in the first stage, we have tubing pickling. The description is included here. What we do in the pickling is, we use a weak inhibited acid, and then this will be pumped to the tubing, and then this spent acid will be lifted to the surface. The second one, we have pre-flush. Normally we will do 10 to 15% HCl. The third one is using acidizing treatment, 1.5 HF to 13.5 HCl. Others are organic clay, or other type of material, or other type of fluids. And after that, we need to push the acid into the formation. That's why we will be using post flush of 10 to 15% HCl. If we have long episons, we will use diverters. That is actually utilized when we have a permeability contrast, and then we will repeat the stage 2 to stage 5, and then we need to have a flowback. After the flowback, we will have another flowback. For your information, this is specifically meant for the fine stabilizer project. And then we will inject this fine stabilizer. We will have some iron control, surfactant, and other additives. So we've done all the compatibility tests with this fine stabilizer. And after that, we will have a post flush to predetermined depth. Normally, the critical matrix depth is about 5 feet. So normally we will inject this, and then we will actually soak this to 15 to 24 hours, and after that we will have a flowback. Okay, so as you can see, we will have tubing pickling, and after that we will have a pre-flush, acidizing, post-flush, and then we will repeat the diverter, and then we will go for the fine stabilizer, and we will push it to the 5 feet. So based on the data that is shown that the sustainability, the half-life of this fine stabilizer is about 15 months. That's why it can actually remain inside the formation for 15 months. That's why the adsorption properties and other chemical properties needs to be actually measured in order to come up with the half-life of such materials. Okay, this is showing you a field procedure in order to actually use this kind of. So if we have, for example, 3 to 4 layers, and we have sliding slide doors, so we will bring up the slit line and pumping unit. After that, we will proceed with the tubing clearance with the slit line, and if the tubing is cleared. If we are able to reach the landing nipple at that specific depth, if not, we will stop the operation in order to make sure that the tubing is clean. If yes, we will go for, make sure that SST number 1, 2, and 4. So this is, this is a specific meant for that well that I worked actually for this, but if your completion is equipped with sliding slide doors, you need to make sure that placement of the acid is going to be inside the actually specific zone, which will be actually achieved by or accessed by a specific SSD. So then we are going to install the plug at X and nipple to make sure that there will be no any actually equipment that will be fall inside the well. And then we will proceed with the injectivity test. If the injectivity test met, we will go for the next step. If not, we will inject above the mask or maximum anticipated surface tubing pressure. After that, we will proceed with the injection of the spacer, which is KCl, and then we will proceed with the injection of main treatment. And then another time, in order to make sure that there will be no mixing between these two chemicals, we will use another time the spacer, and then we will go for the injection of the displacement fluid, ammonium chloride or diesel or other type of material. So we will go for another SSD, and then we will continue the same procedure for the sake of injection inside the specific zone. So this is an example that I plot actually based on the injectivity test that is done in that. So here we can see, as I told you in the quality control, we need to measure the pressure and also all the data that is needed in order to come up with this. So this kind of data is very helpful to see that or to come up with the injectivity and to come up with the pumping pressure that is required for the well. So this is a concluding remarks for the second day. That acidizing is more complex in sandstone than carbonates. Okay, as you can see, matrix acidizing is classified to carbonate and sandstone, and for the precipitates we can have only one single stage. However, for sandstone there will be several stages, and this kind of stages will complicate actually the sandstone acidizing. That's why in our case, acid is chemically consumed and neutralized as a target material is dissolved. In carbonates, the reaction is relatively simple and occurs in a single step. Hydrochloric acid reacts with the carbonates to form a salt, which is, and also carbon dioxide and water. Okay. When acidizing in sandstone with HF, the reaction, are more complex, occurring in 3 stages. In the primary stage, the mud acid react with sand, feldspar, and clays to form silicon fluoride and aluminum fluoride. In the secondary stage, and the silicon fluorides can react with clay and feldspar to release aluminum and silicon precipitates. However, with proper design, formation of these damaging precipitates, which can restrict flow of oil and gas through the formation, can be avoided. In the final state, the remaining aluminum fluorides react until all the remaining acid is consumed. So that's why I was actually coming up with this conclusion in order to show you that actually no software can do the job for you, and you need to be master actually in the design of the stimulation, and each well has its own characteristics, and that's why I was trying my best in order to educate the students about how actually going through the manual calculation for the design, such as stoichiometry and also the kinetics, and coming up with the reaction, and calculating the pre-flush, calculating the post-flush, calculating the main acid, why we go with 15% HCl, how we use the mineral acid, organic acid, and also different types of additives. This is the main strength that you can acquire. After that, you are free to go for the software and do your analysis accordingly. Okay, so I hope that this course was helping you toward understanding and knowing in depth or not in depth, or some surface knowledge about well stimulation, and also the complexities that can actually happen when we do acidizing. Okay, so thank you very much for your attention.